This lecture is about thermal equilibrium. Thermal equilibrium itself is a very simple idea. Two objects are in thermal equilibrium if they have the same temperature. That's all that the word itself means. So these two objects here are both at 20 degrees, so they're at thermal equilibrium, and these two objects are not in thermal equilibrium because they're not at the same temperature. The definition itself is extremely simple. There's a rule that scientists call the Zeroth Law of Thermodynamics that says if A and B are in thermal equilibrium, and B and C are in thermal equilibrium, A and C are also in thermal equilibrium. And if you think about that, that's an incredibly simple intuitive law, because all that that's saying is that if A has the same temperature as B, and B has the same temperature as C, A also has the same temperature as C. Two objects are in thermal contact if heat can move between them. Thermal contact usually just means two objects physically touch. So I can see that these two objects are not in thermal contact with each other because there's an insulating barrier between them, some barrier that insulates heat and prevents the heat from moving through it. And these two objects are in thermal contact because they're making physical contact and heat is moving from one object to the other. Those definitions were very simple. This rule that I'm introducing now is the challenging part of the concept and where the math comes into it. When two objects are in thermal contact, heat will move from the higher temperature to the lower temperature object until the two objects are in thermal equilibrium. Once they reach thermal equilibrium, heat stops moving between them. This rule is true whenever any two objects in the universe enter into thermal contact with each other. When they do, heat begins to move from the higher temperature to the lower temperature object until they have the same temperature. So here I have two objects at different temperatures, as you can see by the thermometers I put next to each one, and I also have a graph of their internal energy below each object. I'm going to move these two objects into thermal contact and observe what this rule tells me about what will happen. So when they enter into thermal contact, heat begins to move from the higher temperature to the lower temperature object, so it will move out of the blue object and into the green object. It will continue to do this until the two temperatures are equal. So the heat moving through specifically means that internal energy is moving from the blue object to the green object. The green object's temperature rises and the blue object's temperature falls. And this continues until the two temperatures are exactly equal. So this is the point where they're exactly equal, and now that they're in thermal equilibrium, heat will stop moving from one object to the other. So when they reach thermal equilibrium, heat stops flowing. You'll notice that the internal energy does not have to be equal because internal energy is different from temperature. But what does have to be equal here is the change in energy, the heat, from one object to the other. The heat lost by the higher temperature object must always equal the heat gained by the lower temperature object. So just to repeat, when two objects are placed in thermal contact, heat flows from the higher temperature to the lower temperature object until both objects are in thermal equilibrium, until they have the same temperature. And as that happens, any heat lost by the higher temperature object is gained by the lower temperature object, because energy is conserved and has to go somewhere. It can't just be created or destroyed. So the final temperatures of the two objects in thermal contact are equal, and the heat lost by the hotter object is equal to the heat gained by the colder object. So these are always true in thermal equilibrium problems. The final temperature of the two objects will always be equal, and the heat lost by one will be equal to the heat gained by the other. And again, notice that the internal energy of the two objects does not have to be equal, but the temperature does. These two facts are enough information to solve for missing information when two materials are placed in thermal contact and allowed to reach thermal equilibrium. There are two types of thermal equilibrium problems we can talk about. Problems where only the temperature changes. These are easier, and we only need to use Q equals mc delta T for those. But there are also problems where we place objects in thermal contact and both the temperature and the phase changes. These are harder, and we would have to use both Q equals mc delta T and Q equals ml for when the phase is changing. So I'm going to give you a few examples of both. This is the first example. We're only dealing with temperature change here. A 2 kilogram piece of metal with a specific heat of 1000 joules per kilogram degree Celsius is at a temperature of 20 degrees Celsius. A 3 kilogram piece of metal with a specific heat of 1,500 joules per kilogram degree Celsius is at a temperature of 80 degrees Celsius. When they are placed in thermal contact, what final temperature will they reach? So I need to use what I know about Q equals mc delta T, and also this new information about thermal equilibrium, where the energy lost from one is gained by the other, and the final temperatures are the same. I'll start by writing down everything I know. This is the information for metal 1, and we're trying to find the final temperature of metal 1. I can connect these using Q equals mc delta T, and this is what that looks like when I plug numbers into that equation. Just one note, I've replaced delta T by T final minus T initial because those two things mean the same thing. The change in temperature is equal to the final temperature minus the initial temperature. Now for metal number 2, this is the information that I have about it. I can plug this information into Q equals mc delta T, and this is what I get here. I know that the change in energy, the heat in metal 1, will be equal to the negative change in metal 2. So Q1 equals negative Q2. So I can plug in my two equations for Q from metal 1 and metal 2 and set them equal to each other. I know that because the two metals are reaching thermal equilibrium, that means that their final temperatures are the same. So I now have an equation with only one missing variable. I'm only missing T final because the T final on both sides is the same T final. So that means that I can just use algebra to isolate T final by itself. And I'm going to assume that at this point you can do that algebra to isolate T final in that equation. When I do that, I find that the final temperature is equal to 62 degrees Celsius. So this is pretty interesting. I can now use what I know about thermal equilibrium to calculate the exact final temperature of any two objects of different mass, different specific heats, and different temperatures that are placed in contact with each other. Example 2 says a 0.03 kilogram piece of metal is heated in a Bunsen burner, and after it is dropped into 0.04 kilograms of 280 Kelvin water. The metal heats the water until the water is at 348 Kelvin. If the specific heat of the metal is 1,230 joules per kilogram Kelvin, and the specific heat of water is 4,180 joules per kilogram Kelvin, what is the temperature of the Bunsen burner flame? I'll write down variables for the metal and for the water. So the metal has a mass of 0.3 kilograms, I have its specific heat, I have its final temperature, and I know that the final temperature of the metal is 348 Kelvin, because it's reaching thermal equilibrium with the water. That's when it stops heating the water. So by the rule of thermal equilibrium, if the metal stops heating the water at 348 Kelvin, the metal must also be at that same temperature for heat to stop flowing. So I know that the final temperature of the metal is 348 Kelvin. And I want to know the initial temperature of the metal because that starting temperature that it had would be the temperature of the Bunsen burner flame that it was taken out of, because the flame was being used to heat the metal until the metal reached thermal equilibrium with the flame, and the metal was then taken out and placed in the water. So the temperature that the metal starts off with in the water will be equal to the temperature of the flame it was in before being placed in the water. Again, I know Q equals mc delta T. I'll rewrite this with my specific variables, but I'm going to hold off on plugging in actual numbers until a little later. I'll now write down what I know about the water. So this is the mass of the water, its specific heat, its final temperature, and its initial temperature. So I actually have all the variables I need to use Q equals mc delta T here. So if I plug this in, I get the heat added to the water is equal to 11,400 joules. And I know that because this is a thermal equilibrium problem, because the metal is exchanging heat with the water, the amount of heat added to the water is equal to the amount of heat lost from the metal. So that means that Q metal is also equal to 11,400 joules, just negative instead of positive. I can now plug that into my equation and solve for the initial temperature of the metal. Now I just use algebra to isolate the initial temperature of the metal, and I get an initial temperature of 3,790 Kelvin. In example 3, an object of mass m1 has a specific heat C1 and an initial temperature of 40 Kelvin. A second object of mass m2 has an initial heat of 110 Kelvin. After they are placed in thermal contact, they reach a temperature of 55 Kelvin. In terms of M1, M2, C1, and the temperatures given, what is the specific heat of the second object? So this is the information I have about object 1. I can see that the change in temperature is positive 15 Kelvin. Plugging that into Q equals mc delta T gets me this. Object 2, this is the information I have about it, so I can see that that change in temperature is negative 55 Kelvin. So this is the information I have when I plug that into Q equals mc delta T. And I can connect those two equations using the fact that their two heats are equal to each other, just one is negative. So when I plug in my values, I get this. And the question is just asking for the specific heat of the second object in terms of the other variables. So if I get C2 by itself, this is what that final equation looks like. 0.27 M1, M2 to the power of negative 1 times C1. So that would be the equation for the specific heat of the second object. I'll now do one example where both temperature and phase changes. These are definitely harder. 1 kilogram of ice at its melting point, 0 degrees Celsius, is added to 10 kilograms of water at 90 degrees Celsius. What is the final temperature of the water after the ice melts? The specific heat of water is 4,186 joules per kilogram degree Celsius, and the latent heat of fusion of water is 334,000 joules per kilogram. Okay, so I'll write down everything that I know. We've got ice, we've got water. This is the mass of the ice, initial temperature of the ice. We need the final temperature of the ice, that's the goal. The latent heat of fusion of the ice. We're dealing with a phase change and a temperature change, so to understand the total amount of energy required, the total heat required, we'll need to use both Q equals ml and Q equals mc delta T. So the total heat added to this ice is going to be the heat required to change its phase, m times L, plus the heat required to change its temperature, mc delta T. So you can see I've written both into that equation. One plus the other will be the total heat added to the ice to change its phase, ml, and then its temperature, mc delta T. The water has a mass of 10. The initial temperature of the water is 90 degrees Celsius. And we're trying to find the final temperature of the water. And this is a temperature change, so we just need to use Q equals mc delta T. So this is what I get for the heat taken out of the water, because the water has a higher temperature compared to the ice, so the heat is moving from the water to the ice. I know that the final temperature of the ice will be equal to the final temperature of the water. This is a little confusing just because the ice will be water when it reaches that same temperature. It's going to completely melt. But I'm just going to refer to that mass that's being heated as the ice, even though it's going to become water. I also know that the heat added to the ice will be equal to the heat taken out of the water. So I can set those two equations equal to each other and plug in my values. And again, I know that the final temperature is the same for both, so I'm just calling that TF in both equations. So you can see that even though this is a very long and complicated equation, there's only one missing variable in it. There's only TF. It appears on both sides, but it's only one variable. And the rule is that if we're only missing one variable in an equation like this, we can always solve for that one variable using algebra. So doing the math to isolate T final by itself gets me a final temperature of 74.6 degrees Celsius. So if you take 1 kilogram of ice at 0 degrees Celsius and drop it into 10 kilograms of water at 90 degrees Celsius and allow the ice to completely melt into the water is going to reach a final temperature of 74.6 degrees Celsius as a result of dropping in that ice. So that's how you do a thermal equilibrium problem when you're dealing with both a temperature and a phase change.